You ever wonder how AI actually sees a picture? For a long time, the answer was a very specific kind of neural network, one built from the ground up just for images. But what if a machine could learn to read an image, almost like it was a sentence? Well, that's exactly what we're talking about today. We're diving deep into the Vision Transformer, an architecture that made a huge leap from the world of language and completely rewrote the playbook for computer vision.
All right, let's get into it. So here's the plan. We're going to start with why just throwing raw pixels at a transformer is a really bad idea. Then we'll look at the old champ of computer vision. After that, we'll get to the breakthrough idea of treating images like sentences, break down the nuts and bolts of how that works, and finally, figure out why these models are so incredibly hungry for data. First up, the pixel problem. You see, before we can really appreciate just how clever the Vision Transformer is, we have to understand why the most obvious approach, just feeding all the pixels of an image into a regular transformer, is a total non-starter.
I mean, it seems to make sense, right? A transformer is built to handle a sequence of things. An image is, well, just a sequence of pixels. So why not? The problem lies in this brilliant but computationally brutal mechanism at the very core of the transformer, something called self-attention. Self-attention is the secret sauce that makes transformers so powerful. The basic idea is that for every piece of the sequence, it looks at every other piece to understand the context. In language, that means every word gets compared to every other word in the sentence. But for an image, that would mean every single pixel has to compare itself to every other single pixel. So let's put some numbers to this to see why it gets crazy. Let's take a pretty small 256 by 256 pixel image. I mean, that's low res by today's standards. That single tiny image has over 65,000 pixels. That's the length of our sequence. And here's the kicker. To compare every one of those pixels to every other pixel, the model has to build an attention matrix that is 65,536 times 65,536. That comes out to over 4.2 billion calculations. And that's for just one tiny image, in one attention head, in one layer of the network. It's an absolute computational nightmare. This scaling issue just makes the whole raw pixel approach completely impossible. So if the transformer was out, what was in? Well, for decades, the undisputed king of computer vision wasn't a transformer at all. It was a totally different beast, the convolutional neural network, or CNN. Models like ResNet absolutely dominated the field because they were built with some very smart, baked-in assumptions about how images work. We call these inductive biases, and they basically gave CNNs a massive head start.
And it's really interesting to see how these biases work. You can almost think of them as built-in cheat codes. CNNs are essentially hardwired to understand that pixels close to each other are probably related. That's called locality. They're designed to recognize a cat whether it's in the top left or the bottom right of the frame. And they learn in layers, starting with simple things like edges and lines, and then building those up into more complex shapes and eventually whole objects like a face. This makes them super efficient. Okay, and this is where the whole story takes a sharp turn. Researchers were looking at the unbelievable success transformers were having with language, and they asked this wild, game-changing question. What if we could make an image look like a sentence? And this right here is the core idea, and it's summed up perfectly by the title of the original paper. The huge shift in thinking was to stop seeing an image as this massive, computationally impossible grid of individual pixels, and instead see it as a neat, orderly sequence of, well, something else.
The solution was just beautiful in its simplicity. Slice it up. Instead of a sequence of 65,000 pixels, the Vision Transformer, or VIT, chops the image into a grid of smaller, non-overlapping patches, say 16 by 16 pixels each. And just like that, this unmanageable, crazy long sequence becomes a nice, short sequence of what you can think of as image words. This is the brilliant hack that lets the VIT completely sidestep that crippling computational problem we talked about earlier.
So, how does this actually work under the hood? I mean, how do you take a square of pixels and turn it into something a transformer can actually process? It all happens in this really slick pre-processing pipeline. Okay, it's basically a three-step dance. First, as we said, the image gets diced up into that grid of patches. Second, each of those little square patches gets flattened out into one long line of pixel values, and that line is fed into something called a linear projection layer. Now, the job of this layer is to learn how to translate that raw, messy string of pixels into a much more meaningful, high-dimensional vector. But now we have a new problem. By doing that, we've basically thrown all the patches into a bag and shaken it up. The model has no clue where any patch came from. That's where step 3 is absolutely critical. A unique, learnable positional embedding is added to each patch's vector. Think of it like a little tag or a GPS coordinate that tells the model, hey, this patch came from the top left corner, or this one belongs in the middle.
There's one last special ingredient that gets added into the mix. A little vector called the CLS, or classification token. It gets plopped right at the very beginning of our sequence of patches. So why do we need this? Well, since every patch is looking at every other patch, there isn't one single output that represents the whole image. The CLS token acts like a team captain. Its job is to interact with all the other patch vectors, to listen in on their conversations, and to build a single, global summary of the entire image. At the very end, the model just looks at the final state of this one token to make its prediction about what's in the picture. All right, now this is where things get really, really interesting. Because the VIT doesn't have any of those helpful built-in assumptions that CNNs do. If you train it on smaller data sets, it actually does worse. But there's a huge twist in this story, and it all comes down to the raw power of scale.
So remember those cheat codes a CNN has? The Viatot starts with none of them. It's a total blank slate. It has no idea that the sky is usually at the top of a picture or that objects are usually made of connected parts. It has to learn every single one of those rules about our visual world from scratch just by looking at tons and tons of examples. And when you don't have a lot of examples, that's a huge disadvantage.
And this chart, man, this chart just lays it all out perfectly. On the left, you see them trained on ImageNet, which is a big data set, about 1 million images, but for these models, it's medium-sized. And there, the ResNet, with all its helpful biases, wins. But then, look what happens when you pre-train them on JFT 300M, this monstrous data set with 300 million images. The vision transformer doesn't just catch up. It learns the rules of the visual world so well that it blows past the specialized CNN.
So the takeaway here is that the VIT's lack of bias, its blank slate nature, actually becomes its greatest strength, but only at massive scale. Because it's not locked into only looking at nearby pixels, it can learn really complex, long-range relationships that a CNN might miss. You know, like how a tiny patch of a cat's ear on one side of an image is related to the patch of its tail way over on the other side. With enough data, its incredible flexibility to learn any pattern becomes a superpower. Turns out, scale is the ultimate teacher.
Okay, so let's just pull this all together real quick. Vision transformers solve the insane computational cost of raw pixels by chopping images into manageable patches. These patches then get turned into vectors, stamped with their original location, and fed into a standard transformer. But their true power, their secret weapon, is only unlocked when you feed them an enormous amount of data, which lets them learn the rules of vision from the ground up and eventually beat the specialists at their own game. And that leaves us with this one last, kind of mind-bending question. If we can really treat an image like a language, with its own nouns, verbs, and structure, what deeper, more fundamental visual grammar will these models start to uncover as we scale them up from millions of images to billions, or maybe even trillions? The answers they find might just change how we see our own world.